Hi, everybody, and welcome to the second session. Today is Thursday. You guys have seen that for the first session that we had it on Tuesday. I was able to upload it to you guys. It's on the same module, basically the same week, but toward the bottom. And this is going to be the habit from now on. So basically, this is going to be the process through which we process recorded sessions. So after the session is over, usually it takes a little bit of time for the video to become available for me to download. I glance through it, then upload it to YouTube channel. And then after I upload it to YouTube channel, and then Google basically gives it the okay, then I come back in here and put the link to on Canvas. Here is the thing though. The closed captions usually require more time to go through and make sure that they are actually updated. So it takes about a day later. So for today, it should be available by Friday if you really need those. If you don't need them, then you can go ahead and jump in there. Now, this is usually useful for the people who don't attend live the class. However, sometimes even for the people who attend live the class, and they would want to come back and review some of the notes, they might want to do that. They might want to come and look at specific time span, basically, whether it's in the beginning, the middle, or toward the end, and then review it. And after that, they can skip through it. As I said before, last time, it's a good idea, actually, to subscribe to the YouTube channel. That way you will have the first hand at it. The minute it's available, you can access it if you want to. And it's a good practice to have it at least for the entire semester. Then after that, you may want to unsubscribe. So that's really the whole idea behind this thing. So this is just how the process works, okay? In terms of the link that we have from Confer Zoom, for some reason, it's not available at all anywhere on Canvas. So probably it was removed. So the link I sent you guys last time, it's still good. It's valid. The only thing is I made a tweak on it so that it starts at 2:10. And it has to start at 2:10 because I'm tied up, at least on Thursdays, all the way to 2 o'clock. So we really cannot start this class at 2 o'clock on Thursday. So every day now, from Tuesday and Thursday, we should be here at 2:10, okay? So this is the plan for this class. So the link I sent it is a valid one, and this is the same one that we're using right now. So that's in terms of the how the course is basically going. Now, I had some questions also related to the assignments and when they were due. The assignments usually are due the week after. So you really need to look into what those objectives are saying. So let me share the screen. Let me make sure I'm in student view in here. And let me share. Not the screen, actually, share just this app. So in here, if I'm looking at the objectives for this week, it should tell me when these assignments are due. It's a good practice to really pay attention to this, to make sure that you are aware of when these assignments are due. Now, here is the trick about assignments. You should never leave it to the due date and start working on your assignment. This is bad practice. You shouldn't really get yourself into that habit because it's going to, excuse me, with some of these assignments, they require more time and more research. So you cannot really do that. So if it says the 24th, when it's due, including this one, I should really have started on it as soon as possible, okay? So that is one thing. This one has a two parts due dates. There's two due dates, actually. One is August 24th, and the other one is August 27th. So I really should be paying attention to when these things are due. As a matter of fact, as I was saying before, assignments are due usually a week later. Not always, but usually. Sometimes they're due in the same week. Sometimes you have an extended, depending on the type of assignments and so on and so forth, okay? You will see, let me go back into the models. you will see that down the road that we have new assignments like quizzes in here. There's going to be, as a matter of fact, next week. So we really start thinking about them. And they will have a shorter, probably time span when they will do. You have another type of assignment called the homework, and then more of that, and so on and so forth. And then you have the lunar observations and when it's due. This one is showing it's going to be due on November 19th. It may be changed, okay? Because I have to do some calculations to know exactly when is the best time to look at, to see the moon. And based on that, I'm going to give you when is this assignment is due. And this one also is actually a type of assignment that has different components in it. In other words, you'll have a component that is due on this date, and another one on this date, and another one on this date, and another one on this date. At the end, after 4 observations, you compile your report. So this is a long-term, basically, project, and so on and so forth. So the point being in here that every week you will have you have seen it now. You have objectives, a summary of the content. Then there is a discussion assignment that makes sure that you guys are on top of things. And the PowerPoints, in this case, there is only one for you week 3. And in week 2, you have 3. So it varies depending on the topics covered and depending on what needs to be done. So this is basically in general as a layout, so that you guys are aware of things and how they are happening, and so that you're working on them. As I was saying, the objectives is something to pay attention to because it gives you pointers into what is due and when it's due. Okay, so this is something that hopefully you guys are on top of. Okay, let me stop sharing first, and we need to get into the because last time, if you guys remember, we did only unit 5. And to just summarize what we did last time, basically, we spoke of the general patterns in the sky, and we looked at the celestial sphere. In a sense, the celestial sphere is a projection of the Earth, because the Earth has spherical shape. So you take the Earth and you project it above you in all of the directions, and then you have a sphere. Sphere whose radius doesn't matter. Basically, the radius is the distance to where all of these objects are, okay? We argued then that these objects have an element of depth that we can't really represent on that sphere. For example, and I gave that example, Ceres, which is a star part of Canis Major, that star is about 8 light years away from us, versus another one, Betelgeuse, which is a next door constellation, which is part of Orion. Betelgeuse is about 800. No, I'm sorry. It's about 500 light years away from us. Okay, so there is a discrepancy in here, and both of them are represented on the same celestial sphere. As a matter of fact, to give you just a third example, Bellatrix is about 242 light years away from us, which is the same constellation. So there is an element of depth in here that cannot be represented. If you look at the constellation, the 3 stars in the belt, they're actually more than 1,000 light years away from us. And one of them is actually about 2,000 light years away from us. So the element of depth is not represented on the celestial sphere. All we represent are the 2 coordinates. Similar to the latitude and the longitude, we have the declination and the right ascension. The declination is measured in degrees, just like the latitude is measured in degrees. The Earth's equator is 0 degrees in terms of latitude. Take the Earth equator and project it in the celestial sphere, and now all of a sudden you have the celestial equator. Anything above the celestial equator has a positive value, and again, it's in degrees, but that's in declination. Anything below the celestial equator has a negative declination, and that's in degrees also. Now, if we take the Earth and move around on a certain latitude, it doesn't matter which one. Right now, we are at the 34 degrees. So if you go around, you're going to go through 360 degrees. And that is your longitude on the Earth. Okay? So the longitude in this case is going to go the entire circle of 360 degrees. Take that longitude and project it on the celestial sphere, and now all of a sudden you have something similar, except it's called the right ascension. That is one difference. The other difference is the units that is measured with it. Instead of measuring it in degrees, like we do with the longitude, we measure the right ascension with hours. So when we go full circle, we would have done 24 hours, just like the clock. It goes actually 2 circles to make 24 hours. But the point being in here is that the idea is similar, if you wish. So that is how it's represented. Now, in terms of degrees, in terms of units, usually the degree is divided into 60 arc minutes, and the minute is arc minute, that is divided into 60 arc second. In a similar fashion, the 24 hours, each hour is divided into 60 minutes, and every minute is divided into 60 seconds, just like the clock. Okay, that is the right ascension. So we locate objects in the sky based on this units. Okay, that's how we represent them. That's how we refer to them. As a matter of fact, let me get the stellarium in here going to show you. What is it? Oh no, I have to find it. Okay. Oh, here it is. Let me get the stellarium to show you that any object in the sky is actually represented with these units. Doesn't matter which. And now it's opened up in this window. Let me move it here first. Okay, so let me share with you the screen. Share. Software. So in here, I have that same software that you guys have seen last time. So let me fix this one in space and this one also, that I can. Okay, let me remove the effects of the atmosphere. So it gave me something dark. Any object I pick in here, it doesn't matter which. This is a star. And let me fix the time so that it's not moving in the night sky, so that it's fixed. So we're looking at the same time right now. On my clock, it says 2:22:21. So that's the time. So if I look at this object, when you double click on an object, I now moved out of it. Okay, it centers around it. So when you zoom with the mouse, basically, when you go in and out, this is a star. It's not going to show you any details because, I mean, even with the best telescope, you're going to see a dot at best. Okay, so here is what I'm looking at in here. There is an RADEC. Okay, J2000. That's by convention the date when that star has on March 21st. Okay, that is when we start to measuring the right ascension. It's 13 hours, which is 1 p.m., 20 minutes, and 34.23 seconds. Okay, and the declination is -36 degrees. It's just below the celestial sphere, the equator, the celestial sphere equator, and 42 minutes and 48.3 seconds. Okay, so this is the position of that star. What's the name for it? It's I Centauri. It's basically of the that's what the name for it has, a scientific name. HIP 65109. Okay, I took a random one in here. Okay, when you are referring to stuff in astronomy, please don't refer to the other numbers. Okay, just stick with the first one. Okay, the one that it says the right is in J2000. So that's the one that whenever you're reporting stuff, I know some of you are sitting in my astronomy 125. All the data that you're going to be representing, all the data that you're going to be referring is this unit, the one, the J2000. Okay, that's really the convention. All of the other one, the azimuth and the altitude, all of the others are not, you don't refer to them in here, at least in this case. Okay, although this one is probably sometimes is useful piece of information, because if you look at the grid in the bottom, there is the azimuthal grid and there is the equatorial grid. So we're talking about the equatorial grid in here. Okay, which is more of a convention that we use in here. But the point being in here is This is a star that we can have all of its information, and these are its coordinates. Obviously, the star has a magnitude of 2.75. Remember last time when we said if a magnitude is smaller than 2, I mean, if higher than 2, usually it's kind of hard to see, and that's true. Okay, so this one is almost 3. So this one is actually dimmer than a lot of the other stars that, for example, Rigel or Betelgeuse or any of the other stars that we see. There's another number in here, and we're going to talk about these numbers down the road to understand their significance and what they mean. Its actual magnitude is 1.47, so it's a lot brighter than what appears compared to the other ones. That means it's further away. That means it's farther away than the other objects that we can see. So that's basically some of the things that we talked about last time. So we talked about the right ascension and the declination, and that is useful for us to locate objects in the night sky. So that is basically from Unit 5. Okay. So Unit 5 dealt with the coordinates of objects in the night sky and how they're represented in the celestial sphere. This is the astronomy lab, and we're supposed to have, and we don't. We're supposed to have celestial spheres in here to demo them. I know that our lab needs more stuff, and we've been talking about it so that we can have telescopes and things like that. We have some telescopes in the planetarium, but we don't have one for us in here. So we're trying to acquire some for our students. Okay. So if we're going to do a telescope, we have to move all the way there to the planetarium and use theirs. And they don't have a lot. They only have a handful of them. One of them is a huge, I think, 16-inch telescope, which is impossible to move. I mean, it's fixed telescope. It's a huge one. Okay. So that is the stuff that we have in here. So that's how we locate stuff on the celestial sphere. Okay. I see that about half the class is already enrolled on the online resource from McGraw-Hill for the textbook, and that is not good enough. We really have to have everybody in that class, because you cannot do things. You cannot read the textbook unless you actually have the hard copy of the textbook. Then you probably don't need to do it. As a matter of fact, and I have seen some people starting on that assignment, that is actually a voluntary assignment, so that you guys know. Okay, I'm testing it for another class, so if you want to, you can do that. So at this point, no assignments on the McGraw-Hill website is required. Is that clear? Okay, very good. Thank you, Kira and Gabriel and everybody else. Okay, so you don't have to do it, but you have to have the book. Half of you are not on it already, and that is not good. Okay, we have to have everybody on that site so that we can do our assignments, because there will be assignments, homework assignments and quizzes and stuff that are strictly coming from that book. So we really have to have that resource in addition to reading, which is a requirement in here. Okay. So let me share with you Unit 6. Share again. Okay. So this is Unit 6, and it describes the annual motion of the sun relative to the stars on your horizon. So the sun apparently moves in the background versus the background stars. The reason why it does so is because, first of all, it's not real. It's an apparent motion. What is going on in this case is the Earth is going around the sun, and as it does, it gives you the impression that the sun is going around the Earth. It's like when you are sitting in traffic, for example, or somewhere, and the other car, especially if you're not paying attention, starts to move back or move forward. If it's moving forward, you would have the impression that you're backing up. If you're not careful enough, then you think, oh man, it's the other way. If you have had a chance to go on a bus, for example, or a train, that is actually more apparent. If you're sitting in the train and all of a sudden the other train decides to move, then you, at least you would think that you're actually moving in the opposite direction. That is exactly what's going on in this situation. So what is happening in this case is that the Earth is moving against the background stars, around the sun, giving us the sense that the sun is actually moving. And it's moving, changing its location on the same time, for example, on the same month, from constellation to constellation to constellation, from an asterism to another asterism to another asterism. Okay, from a group of stars to another group of stars to another group of stars, from this shape to another shape of stars, and so on and so forth. Okay, so this is what we are going to be talking about this one, and this is what we refer to that this is the annual cycle of the sun. So, and then recall the dates and names when the sun reached its extreme and midway points. Okay, at some point, the Earth will be on either side of the sun. Because of its tilt, it's going to have a lot of radiation coming in toward the south, for example, or toward the north if we are looking at the other side. So in other words, if I take that this is, I'm taking my phone in here as an example. This is the Earth is tilted. This is the sun. Remember, the sun is emitting in all directions. So remember, the Earth is still tilted. The sun is still tilted in the same direction. So whichever way, it's going to be tilted, but then the radiation is going to matter that way. So let me try to represent it using another thing in here. Let me stop sharing quickly here. And let me put this thing out and let me share the OneNote. Okay. So on my OneNote in here, think of this point in here. If I can, oh man, it's on the wrong screen. Hold on. It has to be on this screen. Okay. So let me share again, OneNote. Okay. So this is where the sun is. This is how the Earth is tilted, and it's going around the sun. The Earth is tilted, so it's not going to change the tilt just because it's on the other side of the sun. So the radiation of the sun is going to hit, in this case, this one is tilted away. So in here, it's going to be its own maximum of exposure. Whereas in this case, this is, by the way, it's still the same Earth in here. So this is tilted away. This is tilted towards the radiation. So the radiation will take a long time, come at an oblique angle. That's really the reason of why you have seasons, is because of this tilt of the Earth in here. The Earth has 23.5 degrees tilt. So this is the plane through which it moves. This is called the ecliptic plane. By the way, here is Mercury, and here is Venus, and here is Mars. Okay, they're all moving on the same plane, more or less, slightly on and off, but they're all on the same plane. So this is the ecliptic plane. This is where everything is moving. As I was saying, because the Earth is going around the sun, give us the impression that the sun is going around the Earth, because you're sitting in the car and having everything as if it's moving around you. Okay, but it's actually the opposite way, so that the Earth is the one that is moving. As it's moving around the sun, this creates the seasons. Now, there are some critical points in here of interest to us. Here is the sun again. The path is not exactly on a spherical shape. Oh man, I couldn't draw that. Okay, let me move all the way down if I can. Ah, what is that? Okay, so here is the sun again. Here is the Earth, and here is the Earth. Okay, think of it as the path is not exactly spherical shape. Anyway, this point in here, when it's close from the sun, and this one is when it's furthest from, this is called the aphelion. And this is the perihelion. This is the winter solstice. Solstice. And this is the summer solstice. This is December 21st. This is June 21st or 20th, depending on the year. Okay. So those are some critical points in here for the passage of the sun. Now, this point in here and this point in here, this one is going, the Earth is moving. So this is March 21st. This is September 21st. This is the spring equinox, and this is the other one. This is the fall equinox. So these points are important, trying to understand the geometry, if you wish, of the path of the Earth. I mean, my drawings are not good, okay? So you have, hopefully you guys realize that this is supposed to be an elliptical shape. Let me see if I have shapes that I can draw from this thing in here. Yeah, here is a shape. No, not that one. Ah, here is a good shape now. This is an exaggeration of the path of the Earth, okay? So this is actually more or less, I mean, it's not that squeezed, okay? It's called the eccentricity. The sun, this is a focal point. This is another focal point. The sun sits in one of the focal points. So the sun is here. This distance is about 147 million kilometers. This distance is about 153 million kilometers. Okay, million kilometers. This is about 90 million miles. Okay, so this is again the winter solstice. This is the summer solstice. This is the equinox, and this is the other equinox. Okay, makes sense? I exaggerated the shape a little bit. It's not that eccentric. As a matter of fact, the shape is very close from the circle, albeit it's not exactly a circle. This is more or less how the shape would look like. I mean, if you see this one up front, you might think that this is actually a circle, but it's slightly off of a circle. Make sense? Yes? Very good. So we're going to define the ecliptic. I already basically defined it for you guys. This is the path, the apparent path of where the sun moves, okay? And then the zodiac, and there are, as I mentioned last time, 12 constellations that are part of the zodiac, but there is actually 13th one that sits between two of them, okay? But usually people, they don't refer to it because it's more convenient to talk about 12 months than 13 months, okay? And then depending on the latitude, how we'll, because of the tilt, okay? And the precession. The way I was describing the Earth earlier, that it's tilted toward one direction than the other, is true. If this is the plane of the Earth, the Earth is not exactly at 90 degrees with it. This is the plane of the ecliptic. The Earth is actually tilted this way compared to the plane. So it's moving at this angle. But this thing is not fixed in time. This is actually changing. The tilt changes. There is a precession, okay? And that precession repeats every 26,000 years or so. And that is part of the cycle that we're going to, actually, there is more than that. There is another one, it's 100,000 and so forth. In other words, because this one is pointing toward the North Pole, toward Polaris. In other words, Polaris is not always in the North Pole for us. The North Pole changes. In about 13,000 years from now, Polaris is not going to be in the north. It's not going to point toward the North Pole is not going to point toward the Polaris. It's going to point toward Vega, which is another star. Okay, so this changes. Sometime in the future, you might not even have any of these two stars, and it's going to be in between them, and the cycle repeats. So this is basically what the objectives of this this unit are. Okay, so let me share with you the PowerPoint. So again, so this is what I was saying in here earlier, okay, about that rotation. So the sun is here. So during daytime, we see the sun. If I am in August 1st, in this position of the sun, looking at the sun, I will not see anything. So I will not be able to see Cancer in here, the constellation Cancer or Gemini or Leo for that matter during daytime, okay? Because that's the only time I could see them. When the Earth spins around and it becomes nighttime for us, then I can see all of these things, Sagittarius, and Sagittarius is in here, Aquarius and Capricornus and so on and so forth. Maybe these ones are just below the horizon or above the horizon, Scorpius and even Pisces, but that's basically the extent with which we can see. Now, as opposite to that, 6 months from today, when the Earth is in the opposite direction, then the story changes. Okay, then I would not be able to see Sagittarius, for example, Aquarius. I will be able to see when the Earth is pointing in the opposite direction. I would see Cancer, and I would see Gemini, and I would see Leo, and all of the other constellations. So this is basically, since the Earth is going around the sun, that is a constellation we're going to see during nighttime. Okay, unless there is a solar eclipse, of course. If the moon intervenes between us and the sun and blocks the sun view, then we will be able to see the other constellations. So that is basically the only condition we can see them. When the day becomes night, then we will be able to see the other constellation. Okay, that is basically how we have this thing is represented. Again, there are 12 of them if you count them. 1, Virgo, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I miss one? Leo, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 with Cancer. Okay, there are 12 constellations. Okay, the constellation, let me first of all find it in here. Looking for it so that you see exactly what I'm talking about. And let me go to the Wikipedia page for it. Oh no, I want that. Let me take the picture. Okay, so let me stop sharing whatever I was sharing. And let me share with you. Okay, it's called Ophiuchus. I think that's how the name of it is, okay? It's hard to say it, okay? But the point being in here is that it extends all the way to the ecliptic. So you have Scorpius on one side, you have Sagittarius, both of them are part of the signs of the zodiac, but you have this one that extends all the way in there, and the sun goes through it too. So this is your 13th sign of the zodiac. This is the one that is not included as part of the zodiac sign. This is not part of the things that is included when we talk about it. So we talk when we refer to, but it is actually a zodiacal also constellation. Okay. And it's a big one too. It's not a small at all by any stretch of the imagination. Okay, so it's a huge one. It has a lot of this M denominations, which we're going to talk about down the road. You have M9, M107, M62, M19, M14, and these are either globular clusters, group of stars, or galaxies actually, that Mr. Messier, when he looked at the sky, he saw them fuzzy structures in the sky, and he started classifying them M1, M2, M3, and so on and so forth. I mean, he was classifying 1, 2, 3, 4, and so on and so forth, and people appended the name M to it for his name, Messier 19, Messier 62, and so on and so forth. Later on, they were identified as either globular clusters, which is a group of stars that could be hundreds of thousands basically together, case in point Pleiades, for example, or galaxies, okay, like M31 and M33. M33 is actually the Andromeda galaxy, and M31 is Triangulum. So there is all of this classifications in here that is. So this is a big constellation. That's the point I'm trying to say in here, and it's part of the science of the part of the 12. So if you go back into the PowerPoints in here, you will see only we're representing 12 because that's by convention what people agreed to, and it's just to make a little bit the astrologists happy in a sense that we have 12 constellations that the sun goes through in its ecliptic basically path, which is an apparent path. Okay. Then again, the Earth is tilted by 23.5 degrees, as I was saying. In other words, this is the plane where it's supposed to move. The Earth is not exactly at 90 degrees going around. If it were at 90 degrees, the seasons will change completely on Earth. But because it's tilted by 23.5 degrees, then that is really the cause of the seasons, okay? What makes the summers hot and the winter cold, not how far or close the Earth is from the sun. Has very little, if anything at all, effect on the seasons, okay? It's the tilt. So Earth inclination ultimately responsible for the change in seasons. In June, the northern hemisphere is tilted toward the sun. Okay, so look at this path in here. Okay, look at the picture in here. The tilt makes that there is a longer exposure to the northern hemisphere than the southern hemisphere. Okay, the southern hemisphere has a lot more shadow than during at night. Basically, it has longer nights and shorter days. When you have a longer night, you have more time to dissipate the heat, basically, of the sun. When you have less day, you will have less exposure to the sun, so less heating. So, which makes the season on that side of the Earth more like winter, colder. Okay. So this is the season of winter in the southern hemisphere, whereas we have longer daytime, more exposure to the sun, and the rays come actually at a 90 degree. They come straight up down to you. Whereas in the southern hemisphere, they come at an angle. They travel more the atmosphere because they have to go through a lot of atmosphere to get to the surface. So there is less heating because of there is less time for them to heat the Earth. And because of the tilt, so they travel through a longer atmosphere to dissipate that energy before they heat up the ground. So that is why it's hotter during the summer in the northern hemisphere than in the southern hemisphere. The opposite is true on December 21st. The Earth is tilted in that direction so that there is less exposure during daytime to the northern hemisphere. So it's colder. So there is less heat accumulating because less time for it to build up. Furthermore, there is an inclination, and that inclination will cause the rays to travel through a longer atmosphere before heating the ground to begin with. So there is less heat accumulated to begin with because there is less daytime, and there is also an inclination which causes the rays to travel longer before they hit the ground, as opposed to the southern hemisphere, which is exposed to a longer period of time during winter. So they experience the hotter season during our winter and they experience shorter daytime, shorter nighttime, I'm sorry, and longer daytime. So it's the opposite completely, okay? When we are on the equinox, the day is equal to the night, okay? So this is the day and the night are at the same time. Both of them, it doesn't matter which. Are we talking about the summer solstice or the winter solstice? Now, the spring equinox or the fall equinox, okay? So it doesn't matter which, the day is almost the same, okay? Now, some myths, northern summers are warmer because Earth is closer to the sun than in winter. That is not true. That is, a matter of fact, it's the opposite. The Earth is closer to the sun in December than in June. So if the distance really matters, we should have our Decembers hotter than June's, and it's not true. The Earth is 147 million kilometers from the sun in December, shorter than 153, which is about 6 million kilometers further away in June. Had it been the distance that matter, then our winters should really be hot and our summers should be cold, but that's not true. Okay. Furthermore, if the distance is the only player, then it doesn't matter if you are in the northern hemisphere or southern hemisphere, you should have the same weather, the same season, because we are closer to the sun in the December and further away from the sun in June. So why would it matter which one has winter, which one has summer? It would be the same season. So, and that's not true, okay? So this is basically some of the myths. Hopefully that clarifies it. Again, this is the point I was trying to illustrate earlier, trying to explain earlier. Because of the tilt, the rays in here, so this must be the summer, okay? The rays in here, I'm sorry. Yeah, because we're tilting away. So the rays in here are coming at an angle versus in here, they're strictly falling on. Yeah, so this must be the winter in the bottom and the summer is in here in the northern hemisphere. So the rays are coming straight down and the shadows are as short as possible, depending on where you are, depending on your latitude. So the closer you are from the equator, the less shadow you're going to have. But because the rays now are coming straight up to you, then there is no rays in there, there is no shadow in there, versus in here that has long shadows. And the picture flips in the other season. Make sense? Does this make sense? Very good. Very good. So again, these are the dates that we talked about. The ecliptic is again the apparent path of the sun, and this is the celestial equator, and the Earth, the sun passes at least through the celestial equator during these two times during the equinoxes, and then it's above the celestial equator because it's above the Earth equator during that time. So 23.5 degree north, that should put the sun exactly on top of your head during daytime. You should have zero shadow on that day. If you are 23.5 south and you are in the winter, that should put the sun immediately above your head. Anything in here is going to have a shadow, even during noontime. You're going to have a definite shadow. If you have anything in here, at some point during the time of the year, you're going to have a shadow. So the Earth, the sun moves up and down by 23.5 degrees, depending on how far you are. So it travels all the way from negative 23.5 degrees from the equator, all the way to a positive 23.5 degrees in the equator. This is a very important point that we're going to remember down the road, and how the ancients not only knew that the Earth is spherical, but also calculated its radius. Calculated the radius of the Earth using this fact, okay? using this very important fact that at some time, which is the summer solstice, there is no shadow in modern day Aswan in Egypt. And in the same time, there is an 18-degree shadow in modern day Alexandria. Based on that, and based on the distance between Cyan is called at that time, modern day Aswan, and Alexandria, the name never changed. The distance, based on that distance, you can find the radius of the Earth, namely how big the Earth is. Just because of this facts in here. That's amazing. And now people on YouTube trying to argue that the Earth is not, I mean, the ancients did not have YouTube or telescopes or fancy stuff, iPhones or anything like that. And they were able to find the radius of the Earth. Not only that, but they knew that the Earth is actually spherical, okay, sphere with a given radius. Okay. Anyway, so the equinox, we talked about them. That is basically when the sun transitions from northern, I mean, or vice versa, depending on which time you are. We are transitioning right now. We are in August 18th. In about a month and a few days from now, we're going to transition. We're going to move from the northern hemisphere down to the sun, that is going to transition from the northern hemisphere down to the southern hemisphere, basically. At that point, it's going to be the equinox, the spring equinox, and then we're going to move all the way through. Okay, so again, the sun moves around. Okay, in the winter for us, it doesn't really venture a lot from the horizon. So it rises and comes down, and in the summer it stays longer in the sky because it's moving, and this is where the equator is. Okay, at some point in the winter, in the northern hemisphere above a certain degrees, it will not be even rising at all. So they will have all light days in there. And the opposite is true. In the summer, it will never set. I mean, it will rise from the horizon, and it's above the horizon, rise up a little, and then come back to slightly above the horizon and stays there daytime all the time. Okay, never basically goes dark at all. So that is of this, how the sun is moving again. And this is the different positions of the sun throughout the year, okay? The path of the sun, I already described it. If you go day in, day out, and you mark, for example, the position of the sun, you will see that it makes a figure 8, basically in the sky, called an analemma, okay? So that is basically the shape of the sun day in, day out for the entire year. And you can base that and you use it to tell what the time is, actually. Okay, and now I talked about the precession. Okay, so every 26,000 years, the tilt of the axis of the Earth moves around. It's like a top, basically. It's precessing. So the top at some point, right now it's pointing toward Polaris, and the top is moving, and at some point it's going to point toward Vega. And then after 26,000 years, it's going to come back to Polaris and so on and so forth. So this is a regular motion. The tilt of the Earth is not exactly 23.5 degrees. It fluctuates over an extended period of time between 22 and 24 degrees or something like that, 24.5 degrees or something. So it happened to be right now 23.5, but that's an even a longer period of time that it does that. Okay, we're going to talk about the moon and how the moon came out to be, and we will learn that the moon is probably most likely the one that caused the Earth to be tilted. In other words, the moon that has caused the seasons to exist to begin with. I mean, that was a collision between the Earth and another planet that has the size of Mars that caused the creation of the moon, and that collision resulted in the Earth being tilted. So this is basically some of the things that we have in here. Okay. So again, if you look at this picture, let me share with you the picture again. Oh, I'm sharing. Are you guys looking at the PowerPoint? No, no, absolutely not. Sorry. So let me share with you the picture. Again, this is basically what I was talking about in here. Can I the slideshow? Okay. So again, I just want to bring this one. So today, Polaris is the North Pole. Okay. Today, Polaris is the North Pole. And then you guys are looking at the PowerPoint still?
Yeah, we can see the PowerPoint now.
Okay, very good. So the point being in here is that the Earth is moving around. So at some time, it's Thuban that was very close from the North Pole. And it's going to come back in about 26,000 years. At some point, 14,000 years from now, is going to it's going to be close from Vega. So right now, Vega and Polaris are almost opposite to one another. So the constellation changed completely, okay, from Lyra all the way to Ursa Minor right now. So this is changing, but it's changing extremely slow. It takes about 26,000 years, as I was saying. This apparently has dramatic impact on Earth. One of the things that we know has an impact on when it's in here around this location, the Sahara, apparently the Great Sahara in Africa, was a lush green part of Africa. But because the Earth has precessed to this position, now that turned out to be plus all of this vegetations, all of its rivers dried out, all of its basically lakes also evaporated. And is that a cyclic thing that is going to repeat? I don't know. So it seems like there is more rain during sometimes and the whole weather changes so that there is more exposure to that part of Africa. And there's all kinds of indications that that's actually a cyclic event that happens every 26,000 years, rotates basically. Okay, so there is also some research, or at least in the process of being discussed, the impact on North America, especially because of the opposite of what the Sahara is. So again, this has a lot of impact, but it's also on a very long period of time, not our yearly motion, the one that we were talking about earlier. Okay, so again, this is the precession, and this is the cycle. So the North Star 6,000 years ago will not always be the North Star. So that's the point that I was talking about. But Thuban was, okay? Because this is moves around it to very close from Thuban, okay? So these are the two units that were part of this week, okay? I was going to do some problems, but I'm going to assign them first. I'm going to basically discuss the questions with you guys. And then we will have, I will have a short solutions for them. But this is just to get us going. Okay, this is just to get the whole thing going so that we can have more assignments down the road and calculations and things like that. Any questions?
Professor, yeah, for the lab, is that gonna be online as well?
No, no, no. We're meeting here. We're meeting here. Are you section 2 or section 1? Anyway, section 1 meets on Tuesday, section 3 section 2, I'm sorry, section 2 meets on Thursday, and section 1 meets on Tuesday. So if you are -02, we're meeting today at 5:35 in this room.
Okay, yeah, I'm section 2.
Okay. Yeah, so we're meeting today and here on campus in this very same room.
Thank you.
Which is, yeah, room 214 in the physical science building.
Copy that.
Okay. Okay, very good. And also for those who are sitting in the lab, I gave you a link to the lab manual, but I also have the lab manual it's printed in here. So you'll have a hard copy of the same stuff. But of course, the electronic version is actually a little bit better because you can search it, you can look at the content and go straight to the activity. But there is also a printed version in here. Okay. Very good. So these are the two units that we needed to cover this week. Okay. I will release next week, basically sometime and probably Saturday or Sunday, depending on how things go, because I need to make some tweaks and changes to them. And we will have our first other assignments, basically other than the discussions and things that we did so far. It is very important that you guys don't miss the assignment that that is the two assignments that you have from this week. They're extremely important, not only because of the grade, but because also the college look at them in terms of attendance. Because you're an online class, we don't take attendance, but it's your participation and engagement in the class to make sure that you are doing what you're supposed to be doing. So it's very important that you do those assignments. And if you don't, then we have to go by the college rules, basically, into removing some of the students who are sitting in here, and we cannot have them in here. So I will monitor also their participation on Canvas, and I will basically follow up with whatever I need, with whatever you guys need to do to make sure you're doing your assignments. This talk is mainly directed to the people who are watching. This is a recorded session, not for those who are in here, because I'm sure you guys are on top of these things. Sounds good, everybody?
Yeah.
Okay, very good. Okay, thank you, Samantha. Okay, so I'm going to stop the recording. Thank you, Kira. I'm going to, Gabriel. I'm going to stop the recording. And if you guys want to have any, if you have any questions or something like that, not in here, you can always send me the questions, and I'll be more than happy to discuss them. Thank you. Let me stop recording.